Welcome to Module 2 of Computer Engineering. In this part, we will explore how computer engineers move from basic hardware and firmware design to complex system integration. We will also look at advanced areas such as embedded systems, networking, testing, and future technological trends that are shaping the discipline. 2.1 Embedded Systems. An embedded system is a small computer integrated into a larger system to perform a dedicated function. Examples include the control unit inside a washing machine, the system on chip in a smartphone, or the microcontroller in a drone. Computer engineers design these systems to be efficient, reliable, and tailored to specific tasks. Unlike general-purpose computers, embedded systems often run on limited resources but must operate with high reliability. 2.2 Microprocessors and microcontrollers. At the heart of many devices are microprocessors and microcontrollers. A microprocessor is a general-purpose processing unit found in laptops, servers, and desktop computers. A microcontroller, in contrast, is optimized for embedded applications, combining a processor with memory and input-output interfaces in a single chip. Understanding the difference between these two components is critical for computer engineers, as each is suited to particular applications. 2.3 Communication systems and networking. Modern devices rarely work in isolation. They communicate with other devices and networks through wired and wireless systems. Computer engineers design the communication hardware and firmware that enable data exchange. They work with technologies such as Ethernet, Wi-Fi, Bluetooth, cellular systems, and satellite links. Networking knowledge is essential to ensure that devices interconnect seamlessly, securely, and efficiently. 2.4 System integration. System integration involves bringing together different hardware and software components into a single functional system. For example, in designing a smartphone, engineers must integrate the CPU, memory, display, camera, wireless modules, sensors, and power management circuits. The firmware must also harmonize these components to work together without conflict. Effective integration requires testing, debugging, and optimization to achieve performance, reliability, and cost goals. 2.5 Prototyping and testing. Prototyping is the process of creating an early model of a system to test concepts and identify flaws. Computer engineers often build prototypes of microchips, circuits, or entire devices before mass production. Testing ensures that systems meet specifications. It includes stress tests, performance evaluation, and error detection. Because computer systems operate in safety-critical environments, such as medical devices or aircraft, testing is an indispensable stage in engineering. 2.6 Future trends in computer engineering. The field of computer engineering continues to evolve rapidly. Some emerging areas include artificial intelligence hardware, designing chips specialized for machine learning tasks, such as neural network processors. Quantum computing, developing systems that exploit quantum mechanics for computation far beyond classical limits. Edge computing and IoT, building low-power, distributed systems that bring computation closer to users and sensors. Biocomputing and neuromorphic systems, exploring how biological systems and brain-inspired architectures can revolutionize computing. Sustainable and green computing, creating energy-efficient systems to reduce environmental impact. These trends highlight how computer engineering is not static but constantly pushing boundaries. 2.7 The human and ethical side of computer engineering. Computer engineers must also consider ethical and social responsibilities. Devices and systems they design impact privacy, security, and human behavior. Engineers must address concerns such as data protection and cybersecurity, accessibility and inclusivity in device design, minimizing environmental impact, ensuring safety in critical applications. A responsible computer engineer balances innovation with these broader considerations. Module 2 Summary. In this module, we expanded our understanding of computer engineering into advanced areas. We studied embedded systems, microprocessors and microcontrollers, networking, system integration, prototyping, and testing. We also examine future trends and the ethical dimensions of the field. We have now completed the course on computer engineering. In Module 1, we introduced the foundations, the blend of computer science and electrical engineering, the role of hardware and firmware, application areas, and the required skill set. In Module 2, we looked at advanced concepts, embedded systems, microprocessors, communication, system integration, prototyping, future trends, and ethics. Together, these two modules provide a comprehensive overview of computer engineering, from its roots in fundamental science and engineering to its modern applications and future directions.